Today we're going on with 1D motion. I'm going to get to energy, which I didn't get to last lecture and I intended to. And we're going to start our world of iClicker quizzes. So quiz number 1. Today you can work in groups of up to 2, or you can work by yourself. The quiz is, you've got some force acting on a particle in 1D, and we're given that the force is of this form, with c and lambda both not equal to 0, and you want to know which of those things, A through E, is correct. A, B, C, D, E. Okay, and let's give you 2 minutes to work on this. And let me flush the vote, so we get. I'll be able to see how many people have voted. Yes, what's the question? The question is, given this information, with c and lambda both not equal to 0, which of these things is true? Yes?
When it says about 0?
Yes?
About x equals 0?
Okay, let's see how we're doing here. Raise your hand if you have not voted yet. Okay, we're going to lock up this vote. Ready? If I stop, I click on stop. Okay, now well, more than 25% of you, no, less than 20, more than 20% of you got it right. So we'll do this example in class, and you'll see how this goes, and you'll see what is the mistake that you made. It certainly is an intuitive, quick answer to think we've got an oscillating force, therefore we have an oscillating everything, and that's why I put the quiz up here, because if you knew the answers to all the questions already, there'd be no point in taking this course, except for to get credit for it. So I'll show you how that goes. It's kind of an easy thing. Okay, before we get to that, we're going to print the book. It's about 600 pages. That's the dynamics part of the thing, which is online. It's not going to include all the things which are in the statics book. If you want those things, you can read them online, or if you were in statics last semester, you can read the thing in the printout, or if I get requests for it, we can print out more statics books for those of you who don't have it. My reading of the course evaluations from last semester is that those who most complained about the book tended to be people who did not have a hard copy. Now, I don't know whether there's what the causality is there, but my sense is when I talk to friends and colleagues is that usually when we want to read things carefully, we print them out. So I think that my recommendation is to print it out. There's no profit in this for anybody except for the printers. Anyway, so I'd like to do a survey to try to estimate the amount of printings. If they don't print enough, you can put in a request, but you won't get the book for another several days or a week or something like that. So I'd like to print about the right amount, but they're conservative, the printers, because they lose money if there are any books that are not sold. So this is the probability that you will buy the book, and you're going to vote up there, and I'm going to keep track of those numbers. So any questions about the book? So what will it look like, by the way? It'll look like the statics book last semester. I spent an extra $2, or I spent an extra $2 of your money to get a spiral bounding instead of a comb binding. My experience is that comb bindings just always fall apart. And these, I think, did not fall apart. Is that correct? Did anybody have trouble with this falling apart last semester? You did? What? Did not have trouble, but comb bindings seems like people always have trouble with. So anyway, for an extra $2, it's a good quality binding, full color cover, different photograph. Okay, any questions about the book? Yes?
How
much does it weigh? It'll weigh about 50% more than this one. 40% more than this one. So what's that? I'd say about a kilogram. Any other questions? Okay, so please vote here and let me just keep track of these numbers. You can't vote. Okay, now vote. Any more votes? Okay. Okay. Any other questions about course logistics? Anything that's happening in the course? Okay. So we're still doing 1D motion. The overall picture we have of this thing is that we have an x, we have some mass here, and we have some force. And our sign convention always has to be, for these 1D problems, that force, position, velocity, and acceleration are all in the same direction. Now the general problem is that somehow this force is specified. We're not going to get anywhere unless somebody tells us what it is, but they can give it to us in various forms. So the general problem is that the force, somebody might tell us, for example, what the force is as a function of time. But they might not. Like here's an example where force is given as a function of time at the beginning of the lecture. Somebody might give us force as a function of position. For example, spring force or gravity force, it depends on where you are and not on what time it is. Of course, it varies with time as something moves, but it's specified as a function of position. Or it might be that the force is specified as a function of velocity, that there's a drag force which depends on the speed, for example. Or it might be some mixture of these things. So that means that our general problem is when we start with F equals ma, this turns into the problem dv dt is equal to 1 over m, some function of x vt. I'll put it in the other order. So that's our general problem. If you specify that function on the right-hand side, we want to find the motion. Now, once it's specified, this is easy to do on the computer. In fact, the program I wrote in class last time, you just have to change one part of one line to put in any function of position, velocity, and time. You just have to put that function in that line, and that tells us how the thing moves. That is, if we think of the equation F equals ma, like all differential equations, as crystal balls which tell us the future, they tell us the future if we know what the rules are. The rules are that the force depends on the state in the future, what time it is, where things are, how fast they're moving. Then we can move forwards in time, and we know that the velocity a little bit later will be the velocity at the present time plus this thing times delta time. The position a little bit later will be the current position times the current velocity. And now we are at a new time, and we can integrate forwards again to figure out the new position, new velocity, and so on and so on. And that's what they call integration or solution of the differential equation. And that thing I just described is Euler's method for solving the differential equation. So it's easy on the computer, but whether or not it's easy on the computer, you'd like to understand something about pencil and paper solutions. And even if you don't want to do pencil and paper solutions, there's some general facts which are good to know. So the first and probably most important of these has to do with energy and power. So we have energy and power. And you know from probably elementary school, certainly from physics classes and freshman physics, there's something called conservation of energy. This has various forms in various systems. In this case, for one-dimensional mechanics, it's something that we can derive from the laws of mechanics. In general, conservation of energy for general systems is not something we can derive from the laws of mechanics, but in this case, it is something. So how does it work? Is you say, we have this equation F equals ma, and what we can do is we can multiply both sides by v, and then we can look at this term a and think of that a is equal to dv dt. Then we can look at this term here, and is dv dt, v times dv dt, and we make the observation that this is 1/2 of d by dt of v squared. Why do we make that observation? Is because somebody did it before and we remember it. Or if you want, you can do the integration and figure that out. Then that whole thing then tells us that F times v is equal to 1/2 of d by dt of, it's equal to d by dt of 1/2 mv squared. So that's the simplest form of conservation of energy in one-dimensional mechanics. It's probably the simplest form of conservation of energy, period, in all of science. And it says that the power, so this thing we can call power, is equal to the rate of change of kinetic energy. So power equals rate of change of kinetic energy. And this is a general result, and it does not depend on whether the forces are so-called conservative or not conservative. In other words, this works, this is true for all F, true for all F of x v t. So it does not depend on conservative forces. That's the simplest energy equation, is that the power of all the forces is equal to the rate of change of kinetic energy. Now we can integrate this in time. We can call this equation 1. We can take equation 1 and integrate it in time, and it says the integral of power with respect to time from, say, one time to another is equal to the change in the kinetic energy. And that's still true for arbitrary systems. doesn't depend on what the force is as a function of time position. The total work, this thing is called work, is equal to the change in kinetic energy. So work is equal to change in kinetic energy. Now this form is not the form which is used most often in elementary physics, because it's not the form for which you can do the most simple problems, of which there are too many in high school physics classes. The form which is used most often in these classes is you say, let's look at the work term. And the work term is this integral of force times velocity dt. And velocity, is dx dt. And so we can say that's the integral of f dx. So the integral of force with respect to displacement is a change in kinetic energy. So this gives us our standard definitions of work. On the one hand, it's the integral of p dt. On the other hand, it's the integral of f dx. Now, this is still true in general. The thing is that equation on the right, that last term, is a deceptive equation, because if f is given as a function of x, v, and t, you can't do the integral until you know the solution. So, in general, you can't evaluate the integrals until you know the solution, until you know x of t and v of t. That is, in order to make use of this, you have to first solve the differential equation. On the other hand, there is a special case, famous set of special cases, in which you can do the integral ahead of time, and that means you can use it to help you solve the equations. And this is a special case of conservative forces. And in 1D, the word conservative means that f is equal to a function of position alone. So if the force is just a position of position, then this becomes f as a function of x, then this becomes an explicit integral of the type that you can solve if the force is a simple function of position, doing integrals like you did in Math 191. So some examples are, well, let me just go one more step before I go to examples. So now we're going to define something which we're going to call v, and I'd rather call it e sub p, and that's going to be minus the integral from 0 to x of f of x dx, and we have to put a prime there. And this thing we call the potential energy, and I'll tell you why it's called potential energy in a second. The reason it's called potential energy is because then we have this work thing is equal to minus the change in potential energy. So work is equal to minus the change in this thing called potential energy. So now we go back to our work energy equation. So look at the work energy equation. The work energy equation, which says that the work is equal to the change in the kinetic energy. Now we have minus the change in potential energy equals the change in kinetic energy. And that means that the change in the potential energy plus the change in the kinetic energy is equal to 0. And this is what people call conservation of energy. Another way to say it is that the total energy, which we define to be the potential energy plus the kinetic energy, is equal to a constant. So if the force is given as a function of position, and you know it's a given function of position, it doesn't matter what the velocity and time is. Of course, no matter what the force is, it varies from point to point during the motion. But this is saying something different. It varies to point in a way such that the force at a given position is the same no matter what the motion turned out to be. Then you have this energy is a constant. Now you say, why is this thing called potential energy? The reason it's called potential energy is that it's, if we just think fundamentally, the most fundamental definition of energy we have is kinetic energy. Then this says that if you give this up, it turns into this. So anything you have here is potentially turnable into kinetic energy. That's where the expression potential energy comes from. Okay, so now what are examples of this? The most famous example from, say, high school physics is that if we're going to call x down like this, we say that the force is equal to a constant mg. And if the force is a constant mg, here we have this force is equal to mg, then that implies that the potential energy associated with this force is equal to, in the notation I have here, minus mgx. There's an arbitrary constant, which is where I put the 0, but let's just say I put the 0 right here where I put 0. So my definition of potential energy goes from 0 up to x. And the way people usually write this is mgh. Minus x is how far up you go, and this then gives you the conservation of energy for gravity problems, which is that E total is equal to 1/2 mv squared plus mgh is equal to a constant. And you can solve various problems of particles falling without air friction using this result. Okay, any questions about this example or anything so far? Yes?
The EP, when x is 0, shouldn't it be sign number, so shouldn't it be 1 minus x times mg?
Shouldn't the potential energy...
Potential energy and the negative mgx, when x is 0, the potential energy is 0, shouldn't the potential energy be like 1?
No, let's see, I didn't follow what you just said. But let me just write it out here. Potential energy is equal to the integral from 0 to x of minus of f of x dx. So this is equal to minus the integral from 0 to x of mg dx, which is equal to minus mgx. There's no constant left over in that. I don't know if that addresses your question or not.
Well, when you said that like the x equals to 0 is at the top,
Yes?
so x goes downwards.
So x grows downwards, so the potential energy gets less and less the bigger x is.
But it doesn't in that case. Oh, okay, I guess more negative.
Okay, the minus signs are confusing in potential energy. I have to think it through from scratch every time myself. But if you remember the word potential energy, you can make the signs work out for you. That it must be that if it goes from here down to here, the kinetic energy is going to increase, so the potential energy has to decrease. So this has to be the direction of decreasing potential energy. Another question? Okay, so this is one famous example, which is gravity. And this is what we call near-Earth gravity. And any constant force will work out the same way. An interesting case of constant force that works out the same way is frictional drag. If something is sliding with a constant frictional drag, it has a potential energy associated with it. Even though friction is dissipative and you don't think of energy as being conserved, mathematically you can go through it as if it's a conservative problem, at least so long as sliding is occurring. If there's a transition from sliding one direction to another direction, or from sliding to no sliding, that's no longer true. Here's another example, famous example, is that if you have something on a spring like so, and we're doing one-dimensional problems. And this is some k here like this, and there's some place where the spring is relaxed over here. We'll call that place x. If we draw a free body diagram of this mass, then there's a tension in that spring, and that tension is equal to k times how far the spring is stretched. And from that we say that we have a force which is equal to minus kx, where we're taking a force to be positive to the right. So if it's displaced to the right, the force is negative. If it's displaced to the left, there will be a positive force to the right. And from this, we can then integrate to get that the potential energy associated with this force is 1/2 kx squared. And then the third famous example, now I have to get into the erasing routine here. The third most famous example is not near Earth gravity. So this is still an example of potential energy, where the force is equal to a minus m over x squared, and that's an mmg. And what we're going to do is we have a capital M here, we have a little m here. Let's measure x in this direction. And this is the case of, say, the sun and the earth. If we want to think of this as a one-dimensional problem, we're imagining the sun and the earth, and they're not rotating around each other, they're just in a line. And we're interested, for example, is what would the motion of the earth be if we just let go of it some distance from the sun? How would it fall into the sun? Well, it would fall according to this relationship here. We have this force here and this force here. Here, the force to the right is minus mm over x squared. Here we could write m over x squared times g. Now this thing has with it associated a potential energy, and the potential energy of this is this really funny potential energy. It's m over x times g. So the potential energy has this funny shape to it. If we make a plot of the potential energy versus position, it looks like so. It's always negative. What do you mean negative potential energy? Well, the value, the absolute value, in terms of any constant you add, has no effect on the mechanics. So when something is at infinity, you say it has zero potential energy, and then the potential energy goes down and down and down as the Earth gets closer and closer to the sun. And if it was falling in, the kinetic energy gets bigger and bigger. And as the Earth falls into the sun, the kinetic energy goes to the infinity. So as Earth falls into the sun, the kinetic energy goes to infinity. Another way to say that is the velocity would go to infinity. So we could go and try and solve the differential equation and figure out what is the velocity as a function of time. This is a kind of problem that Newton was very good at and solved lots of problems like this. Oh, so, okay, any questions about these examples? I'm going to erase this board next. So quickly, let me know if you have any questions about this board. Ready? Okay. So that's it for potential energy. Let me talk about some other special cases. So another special case is that F is equal to only a function of time. So one example of this would be the quiz question I just gave you. So let's just do that quiz question and see how that works out. F, in that case, I said was C e to the, sine of lambda t. Now, just to make it so that we can get used to dealing with units, let's just say that m is 2 kilograms. Let's say C is 3 newtons per what? What would the units of this thing be? This is dimensionless. That has to just be 3 newtons. That's the units of the C. And let's say the lambda is equal to 4 per second. So it has to be units of 1 over time, because the argument of any transcendental function has to be dimensionless for it to make sense. Who knows what the sine of 1 second is? It's not a well-defined thing. The sine function needs as an argument a dimensionless quantity. Okay, so let's add to this example the initial conditions that x of 0 is equal to 0 and v of 0 is equal to 0, and then this becomes the quiz problem, and now we're just going to work out in detail what the quiz problem is. Before I do that, let me just point out that if f is equal to f of t, then that implies that solution for v of t, and then x of t is integration from 1910. That is, all problems of this type are exactly problems straight out of Math 191. They're just, to do the problem, you just do a direct integration. Not integration in the general sense that we say solving a differential equation is integrating. Moving forward in time, we can think of as a sort of generalization of integration, which we call integration. Here I mean integration in the exact sense of a homework problem from Math 191. Now, if I give too hard a function here, it becomes a hard problem in Math 191, and it's very easy to give functions here where it's such a hard problem that you can't do it, and I can't do it, and Ramanujan can't do it, and nobody can do it. That is, they can't do it in the sense of writing a formula. You can still do it in the sense of finding a computer solution and finding out what function of time the position and velocity will be. We just can't write a formula for it. Okay, any questions with this before I go ahead? About the difference between numerical solution, analytic solution, Math 191, and so on. Okay, so now I just want to plow ahead and do this problem as if it's from Math 191, which is what I sort of asked you to do quickly, but I didn't really give you enough time to do all the algebraic details. Those of you who got the problem right, in this case, right meant, I think, D. Is anybody who got the problem right somebody who actually just went through and did the math? Or do you just sort of thought about it and kind of got the answer? Okay, so let's just see how this works. This turns into dv dt is equal to 1 over m times f, but f we're specifying here as equal to c sine of lambda t. And I'm going to do the math in detail, and then we're going to get our answer, which is that the position goes to infinity as time goes to infinity. It will be a math result, and then I'll try and go back and make it intuitive for you, why we get that result. Okay, so here we are. We got a function of time, which we're trying to find. Velocity is a function of time, and it's all somebody's given us as the derivative. That's the Math 191 question. How do you solve this Math 191 question? I mean, there are various ways to think about it notationally. You can write dv is equal to 1 over m c over m sine of lambda t dt, and then you can add up on both sides. This is sloppy calculus, but it works right. And then if we want to be very careful about it, we can say we're going to integrate from 0 up to the velocity, and we're going to go from one time to another time, and therefore we have to integrate with dummy variables like that. So this tells us then that the velocity at time equals 0, whereas the velocity we're interested in minus the velocity at time equals 0 is equal to this integral. And what is this integral? It's c over m. Now we have to take the integral of the sine function, which is the cosine function. That is the cosine function times lambda divided by lambda. Cosine function divided by lambda. So this is cosine lambda t divided by lambda, but there's a minus sign in there. And then we're going to evaluate this between 0 and t. And we've got our t prime like so. Now we specified that the velocity at time equals 0 is 0, so that just turns into v. We have a c over m, and now we have what is this function of time here for the velocity? We've got a lower limit and an upper limit of integration. The lower limit of integration is cosine of 0, which is 1, and we're going to have a minus that 1, so we're going to have a minus sign for this one. This is going to have a minus in it because it's up here like that. So altogether we get a minus sign up here, and we get a 1 minus cosine of, we get a lambda out front here, and we get 1 minus cosine of lambda t. Okay, so now let's look at what the velocity looks like as a function of time if we make a plot of that thing. Well, to start with, we could have plotted the acceleration versus time just to get intuition for it. And then we have our velocity as a function of time, which is the integral of that. And what we were given for the acceleration as a function of time was a sine wave. So this was the acceleration as a function of time out here to a time which was, let's see, a little bit less than 1 second. Yeah?
I think you have too many minus signs.
I have too many minus signs.
It's either cosine minus 1 or negative. Or it's either negative cosine minus 1 or negative cosine.
How about like that? Okay, so what do we expect just intuitively? Remember, this acceleration is the force divided by the mass. We start out with 0 velocity. Then we have what's the acceleration at this time is 0. So that means the rate of change of velocity is 0. So this function starts out here with 0 slope. It starts to go up. It has a maximum slope right at that point. Then at this point it has 0 slope again. So it goes down to 0 slope like this. Then it starts to get negative, and it goes down like so, and so on. So that's what the velocity looks like as a function of time. All right, so the velocity is oscillating, but it's not oscillating about 0. So those of you who thought the velocity is oscillating about 0, it's not correct. Why isn't it oscillating about 0? Here we have the acceleration oscillating about 0, is because we start out with a positive acceleration. So we build up some velocity, which we keep for all time in the solution. Okay, now we want to go the next step and look at position as a function of time. So we have x as a function of time. Let me just write it a different way. It's x of 0 plus the integral from 0 to t of velocity as a function of time, dt. X of 0 we were told was 0, so I don't even have to write that down. We're given that initial condition. Then this velocity as a function of time is this thing we just worked out. It's c over lambda m. So I can put my c over lambda m in front, times the stuff on the inside, 1 minus cosine of lambda t. T prime, I've got to put dt prime. So now we have to do this integral. So we have c over, not a good piece of chalk there. We have c over lambda m. And before I go on, you can fill in the blanks there, and then we'll compare. While you're filling in the blanks, I'll erase the board. Any questions about this next board here? Now I'm in big trouble because I didn't do that soon enough. Okay, so now we have to do this integral. The integral of 1 is t, which we'll call t prime. The integral of minus cosine is minus sine. So we have minus sine turns into a plus sine of lambda t prime divided by lambda. And then we do this between 0 and t. Okay. Then we have c over lambda m. The integral of cosine is sine, and that leaves that as a minus there, which I like. Sine evaluated at 0 is 0, so then this just turns into t minus sine of lambda t divided by lambda. So now we can make a plot of that function. Here's t and here's x. It starts out with this competition between t and sine of lambda t. This has a slope of 1. This has a slope of lambda, but we're dividing by lambda, so this whole thing has a slope of minus 1. So this starts out with a slope of 0, and then it oscillates, but it oscillates about this curve here. The slope of this curve here is 1 divided by c over lambda times m. Okay, so the position goes to infinity and beyond. And that's that. So again, I said this is what the math gives. This is why the answer to this question was that the position goes to infinity as time goes to infinity. The reason the position goes to infinity is that the average velocity is not 0. So here's the average velocity. Average velocity, we can call it v bar, is this quantity here. So let's say we wanted to calculate v bar. The average velocity is equal to v bar. What is the average velocity? That's the slope of this line, or going back here to the position, this is the velocity oscillating about this value here, c over lambda m. So the average velocity in this case is c over lambda m, and I'm going to use this as an excuse just to go through a small units calculation. This, I said c was what, 3 newtons? So this turns into 3 newtons divided by, let's see, lambda we said was 4 per second. And then this gets multiplied by m, which we said was 2 kilograms. And we're supposed to get out of this a velocity. How can we get a velocity out of this? We can multiply it by 1. We want to multiply it by 1 in such a way that we think it's going to work out well. If we multiply by the wrong kind of 1, it's still correct. It just doesn't help us work things out. What's the right kind of 1 here is we put 1 newton. And on the top we put 1 kilogram meter per second squared. Okay, so this whole quantity here is 1. And then if we want to see if everything works out, newtons cancels newtons, kilograms cancels kilograms, the second squared cancels the second, and we're left with a meters per second. So we have our 3 divided by 8 meters per second. That would be the average velocity. If we wanted to figure out the size of the oscillations, of the position oscillations, the oscillations in position are equal to 2 times the amplitude of this cosine wave, which is c over lambda squared m. And then we can do that calculation too. That gives me a c 2 times 3 newtons. And then we have a lambda squared, which is 4 per second, multiplied by m, which is 2 kilograms. And this was squared here. And what happens with these units is exactly the same thing as happened with these units, but we have an extra second on the top. Here we had meters per second, so this turns into meters. So then this is equal to 6/32 meters. So it oscillates about 20 centimeters back and forth. So it goes at a constant speed, on average, with an oscillation about that constant speed of 20 centimeters. The speed always goes to 0. So the motion of this thing, if you start, let's just take this as our mass here, we're going to suddenly apply a sinusoidal force to it. It will start to accelerate, and it will come to a stop. Then it will accelerate and come to a stop, and accelerate and come to a stop. And what you see is in the long run, its position is increasing linearly in time. In the long run, it's got an average speed, which we just figured out there was a little less than 1/2 meter per second. In the long run, the position is going to infinity, but it's going there in this oscillatory way. Oscillatory compared to what? There's a constant velocity motion here, and there's this oscillating motion. And you say, how big is that oscillation relative to the constant velocity motion? And that's that amplitude of that position oscillation, which I just calculated. Okay, yes, question?
I was confused because you said the average velocity is c over lambda f. I don't understand how you got that. Is that the maximum velocity? Because like velocity is equal to average.
So here you have this velocity, and what you have is this velocity gets multiplied by this. This quantity goes back and forth between plus and minus 1.
Right.
So that means this thing goes up to 2 and down to 0, and the average is just the 1 here.
Okay, never mind.
Is that good enough? Okay, any other questions? According to my calculations, there's 3,000 seconds have already passed, and that means the lecture's over. Right?